Hello, everybody, and welcome to the first serverless meetup here in Graz. We will also have a live stream today. That's the reason why we are already starting, because we said that the stream will start at 6 p.m. So thank you for coming. It's amazing that there are so many people here for our first meetup. I also want to say hello to everybody who is watching online our stream. I've been told that there are people around Europe watching today. We would like to give you and everybody here in Graz the best possible experience. So one thing regarding questions during the talks, please put your questions to the end of the talk so that I can walk around with the mic. Even if you cannot hear me talking through the mic here in the room, all the people watching can only hear you if you speak through the mic. And for you guys watching online, please, if you have questions, just log into your YouTube account, type in your questions, and we will then pass it to our speakers. My name is Jürgen Blematl, and I'm the director of AURENA Tech. This is our team, AURENA Tech. We are the creators of AURENA AT. AURENA AT is currently the most successful and fastest growing online auction platform in Austria. AURENA AT was one of the first customer-facing single-page applications in e-commerce, and it's a real-time online auction platform where everything you see happens in real time and you have a live interaction. This gives us the possibility to give our users a new level of auction experience, and this is one of our biggest competitive advantage. So besides technology and user experience, what is interesting about AURENA? AURENA, as I said, we develop and we create this platform, but from a business perspective, what is interesting is we are an e-commerce company, but we do no shipping, we do no warehousing. So everything you buy on AURENA, on the auction platform, you have to pick up at the seller side. So no shipping, no warehousing at all. And the second thing which is interesting about AURENA is we meet a customer need which no other e-commerce platform in Europe meets. We can sell off hundreds and thousands of lots, unique lots and items in just 1 week. So just think about, you want to move with your flat to a new flat, for example, and you want to get rid of all the furniture. If you try to sell it on Willhaben or some second-hand platform, I think it will take you, I don't know, month, maybe half a year, and even after then, you may have to get a company which is scrapping all the rest that you couldn't sell. On AURENA, we are able to sell everything and every product within just 2 weeks, and you get really good money out of it. And when I say we sell everything, I really mean we can sell everything. Let's just have a look what we sell or sold in the last weeks and months. For example, a coach, pairs of socks, a box of faulty hand tools, a nearly brand new i8 BMW, a portable toilet, a non-portable toilet, CNC machinery, excavators, shoes, fire truck, frozen roast beef, that's one of my favorite, the barbecue, and then, of course, the grade of beer. So really, you saw there the prices, so somebody paid €13.80 for this box of beer. So, as I said, we really sell everything. We're not just selling stuff of private persons, we especially sell items of large-scale industries, large-scale business. So we sell off companies that go out of business, we sell off companies or businesses that retire, so really large-scale lots. So let's look to some numbers. AURENA 2019, we had a net transaction value at around 30 million euros with a digital team of 9 people. So we could double our sales from 2018 to 2019. So when you see here, we had placed bids around 900,000 in 1 year. we got around 20,000 new bidders, and we sold around approximately 135,000 lots in this time. So how did everything start at AURENA, and why are we here today? Why are we organizing this meetup? Why is it so important for us to build up the community here? Let's have a look at the timeline. We at AURENA, we started in 2012 as a traditional auction house. So we sold items like you maybe know from the movies in a big auction hall where there is one person, an auctioneer, selling all the stuff. We then said in 2012 we want to move to online auctions because we want to reach a broader audience, because we want to be more efficient. But from the first day on, when we conducted online auctions, we were never satisfied with the user experience, because in online auctions, and especially with eBay, you never have this live auction feeling where people are really thrilled and competing each other. So you don't have that feeling, and so we were never satisfied with what we got from the live auction, from the online auction. So that was the reason why in November 2014, the company was around 10 people in total back then. We evaluated all available online auction software, and we came to the same conclusion. There was nothing, no auction platform that met our needs for a special user experience, for a special bidding and auction experience online. That was the time when we decided that we want to build our own platform, that we want to build our own software solution. Back then, there were no technical people at the company, no developer, no designers, no engineer. So we started from the ground, we built up our in-house startup, and then in 2015 started with software development. We went live with AURENA AT, the platform I showed you before, in July 2018. And as I said, in 1 year we could double revenue. The reason was we became much more efficient with our own software. We could conduct the double amount of auctions with the same amount of employees. And on the other hand, due to the good user experience, the good auction experience, we could sell much more items on the platform. In 2019, last year, we started with our business unit AURENA Tech, which is from now on responsible for all the digital development, for the product development, and for all the new products we want to bring to the world. So now, why serverless, and what are we going to do in the next years? Our vision for 2025 is we want to become the largest sell-off platform in Europe. So what we are doing now in Austria, where we are already a market leader, we want to spread to all over Europe. And therefore, we need to have high reliability and high scalability. And that is the reason why last year we started to think about technology. We started to evaluate what kind of technology, which frameworks, even what programming language will we use for the next decade or 5 years. And we came to the conclusion after really, I think, 6 months of evaluation, we came to the conclusion that whenever possible and whenever meaningful, we want to use native serverless frameworks or native serverless functions to be high scalable. So that was the reason. And when we started to build our first prototypes, it was quite easy. But when you come into product development, really reliable product development, everything changes. And we started to understand that there is a lack of experience, that there is a lack of education, that there is even a lack of documentation. So you think there is a big community out there for serverless? We didn't find it. So that's the reason why we said we want to build up a community. We want to start a meetup here in Graz just to bring people together who are interested in serverless and give something back what we learned in our past 6 months and start a community, start to contribute. And what do we want to achieve with our serverless meetup? As I said, first, we want to share our knowledge, our learning curves, our learning journey we had in the past 6 months. And of course, we also want to bring here well-regarded speakers from all over Europe who are experienced in serverless technologies and can tell you about pitfalls and best practice examples. So talking about experts from all over Europe, our special guest this evening is Lars Röwekamp. I'm so happy that you're here today. Hello, Lars. Give him a really big round of applause, please. Lars is one of the, I think, most best well-known microservice expert in Germany. You are a consultant, a trainer. So thank you for being here with us today. You will be talking about
serverless, of course.
Okay.
About some pitfalls, some best practices when it comes to serverless testing, for example, about suitable scenarios when to use serverless or when not to use serverless. I will compare serverless to container technology, when to use serverless instead of container, or when to use container instead of serverless.
Great. So you will give us an overview, and we'll step into.
Yeah, that's it. That's it.
Okay, great. Thank you, Lars.
Thank you.
Thank you.
So I hope I will find my slides on this computer, because it's not my computer. Okay. It's working. Okay, so just put these over there. So welcome to Serverless, the Missing Manual. Welcome everybody here in the room, and also all the people at home at the, looking at the live stream right now. Warm welcome to my company located in the north and the middle of Germany, because they are looking the stream right now too, of course. This is my company. I work for Open Knowledge. We are a software development and IT consulting company, and doing large projects, mostly in enterprise computing and cloud computing area. And we are located in the very north of Germany, a city called Oldenburg, and another location is in Essen, and we call it Ruhrgebiet in Germany. Okay, that's me. And the only important thing about this slide is my title. I'm CIO New Technology. That's very important. And it means that I can play around with cool stuff while my colleagues have to work and earn money. And I spend the money, of course. And doing this, I started several years ago trying out this serverless world, trying out different serverless technologies. And this is the reason why I'm here today. Because I started with several of our customers some serverless projects, and I want to share my experience of these projects today with you. So, of course, I know, because due to the fact we are on a serverless meetup today, everybody of you has at least a small experience of what serverless will be, or serverless is, and how to use it. And I guess most of you have played around with it, or maybe have something in production with serverless. But nevertheless, I want to start with what is serverless, to make sure that we have the same feeling of what we're talking about. And when you take a look at the AWS product side, website, you see something like serverless is run your business code highly available in the cloud in response to events and scale without any servers to manage. And when we take a deeper look at this sentence, we will find something like, first, run your business code. This means that your business code is in the focus from the get-on of this technology. It's about writing code and running code, and not about running servers. So you just write code, bring it to the cloud, and everything else will be done by the cloud. That's the theory. We will learn during this day that the practice is a little bit different. So no servers to provision or manning. And when I talk about servers, I do not talk only about physical hardware or VMs, but also about, for example, application servers. You don't have to care about application servers. And if you use all the cloud platform components like databases, storage systems, and so on, you don't have to care about these servers either. So this means you don't have to care about patches, for example, or security issues, and so on. But this also means, on the other side, you have to trust the cloud provider, that they will do it in a right manner. Built-in high availability and disaster recovery, and as far as I understood the introduction, this is exactly the reason why you chose serverless technology. With the help of serverless technology, you have high availability worldwide, which means you can scale on demand, but you also have redundant availability zones. So this helps if something went wrong On the cloud provider side, you have the possibility of region replicas, so you can reduce latencies if you place your serverless functions and the integration into the cloud components worldwide, and you have something like automatic versioning and easy rollback mechanism if something went wrong. And this is all stuff that you have to do a lot of work if you want to build it by your own. Scale with usage by design, as I said before at the last slide. This is very important if you, for example, have workload with traffic peaks like your auction system, for example, or like a voting system or something like this. If you have unpredictable workload patterns, which means you do not really know when there's a lot of workload and when there's adequate workload. And to be fair, there is normally for all providers a limit given. So if I talk about unlimited scalability, it's not really unlimited. It's limited by your account. But this is mostly done because of security reasons. So it's not allowed to avoid denial of service attacks. They have normally a limit by 1,000 parallel cores, but you can enlarge this and bypass it if you want, with some extra money, of course. Okay. If you see these points I just mentioned, this 4 points I just mentioned, maybe it's cool for the developer or maybe for the DevOps guys, but the management, of course, will say, I'm not really convinced. And for them, the most important thing is you never pay idle. You only pay if there is workload. So you do not pay for hardware or for software service or for something like this. If there is traffic, you pay for it. So if there is business, you pay for it. If there's no business, you don't have to pay for it. Okay. This was a short introduction into what is serverless or what are the main characteristics of serverless, because we will need this later on. If you maybe have some experience with containers and container orchestration, you may ask yourself, okay, why to use serverless when we have containers? Can't we reach all this stuff with container technology and container orchestration too, because we also have unlimited scalability possibilities and so on. And therefore, I want to compare both technologies or both approaches. And the next slides are based on talk by Rajit Sahar, Serverless versus Container. So do yourself a favor, go to YouTube and check this talk out. So what is serverless? I already talked about it. Serverless is a compute server that lets you run code without provisioning or managing servers with the 4 advantages I already talked about. And what is container in contrast to this? Container is standard unit of software that package up code and all its dependencies like libraries, like configuration files, like runtime and so on. And the good thing about containers is that they isolate apps or services and their dependencies. They are portable from one environment to another, to other environments, and they are vendor agnostic. And that's totally different to serverless, because serverless is highly proprietary normally. When we take a deeper look at the environment of serverless is managed by the cloud provider. So the cloud provider cares about scalability, high availability, and so on, and you have nothing to do with any patches of the underlying virtual machines, of hardware, of server technologies, of runtimes, and so on. On the upper side, the container technology, the users control the underlying infrastructure. This means you have some work to do, even if you can use tooling for this, but you have to, for example, care about management and orchestration. You have to make a master node high availability, high available. You have to handle virtual machine failover. In case of Amazon, you have to care about rehydration of Amazon machine images, which means if you want to reuse an older image, you have to bring it up to date. So you have some work to do that you don't have to do on the serverless side. The not so good thing at the serverless environment, serverless side, is that you can't install any software you want. So if you, for example, think you need an application server or something like this, it's not possible. Of course, you can bundle libraries you will need for your business logic, but that's all. At the container side, you can install almost any service, because that's the main idea. You package anything in your container. And the good thing about this is that there are pre-packaged images with different software that are available. So most of the well-known common software you will need during your daily business are already pre-packaged as a container, and you can enlarge them if you want, and combine them, of course. When it comes to configuration of the environment, it's in the serverless world, it's very easy. You choose the memory size, and you choose, there's an amount of runtime duration that is allowed from 1 second. It's not really 1 second, it's milliseconds, 100 milliseconds to several minutes. And for the container side, you have to do a little bit more work, especially if you want to adjust the parameters during runtime. So when we talk about what is a superpower, if we bring all this together, what is the superpower of the one hand side, on the other side? The superpower of serverless is the very easy onboarding, and that is focused on solving your business problems from the get-go. So it's meant to write your code, your business code, bring it to the cloud, and everything is done in theory. If it comes to container, it's more about complete control of your environment and the very, very rich ecosystem. So everything, nearly everything already exists, so you can take it, combine it, and package all your stuff. What are suitable use cases for the different worlds? Serverless shines especially for event-driven architectures, because a serverless function is triggered by an event. And normally they integrate there's a very good native integration with other cloud services, cloud components or cloud services. So when it comes to AWS, for example, you can trigger your serverless function by S3, which is a storage system in AWS, by S3 events. So if anybody put an image or a document or data into S3, there will be an event created, put object event, and you can listen to this event and start your functionality. Or if there's a stream like Kinesis and some data gets into the stream, you can react to this. So you will always find good use cases if there's a high level of integration with all the other cloud services. You can think about these serverless functions as a kind of glue code between the different cloud components. Use cases for containers and container orchestration are more fast software migration to the cloud. So if you have already existing systems like a monolith or something like this with web server or app server infrastructure, and you want to bring this to the cloud, it's very easy to package this into containers and orchestrate them. So it's a different purpose. Serverless also suited very well when the traffic is unpredictable because of the auto-scaling paradigm and because of the pay-per-use mechanism. So if there are peaks, for example, or if the traffic goes like this, it's a good thing or it's a good possibility to use serverless. On the upper side, in the container world, it's more suitable when the traffic is predictable because you pay for the underlying VM. We will see this on the later slide. And if you want to scale, you normally have to scale a totally fully VM. You cannot scale only parts of it, but the whole VM. And this, of course, costs a lot of more money than only have one more Lambda triggered. When it comes to microservices, microservices are a huge hype, still a huge hype, and a lot of companies try to migrate monoliths to microservices. And when we think about this, may serverless be a good combination for this or containers? When it comes to microservices, it seems to be a good solution because the code already is modular. So if you have very small microservices, so what is micro, nano, micro, or it's maybe like a small system. If you have very small microservices, it seems to be the perfect fit. Also because you have a highly API gateway integration. So if you have a typical CRUD microservice, it means somebody triggers via put, delete, read, and so on. You can use the API gateway to translate the RESTful calls into Lambda triggers or serverless triggers and translate the payload, and everything is done automatically. The problem about this is that serverless is meant for event-based architectures, and most monoliths are not event-based but request-response-based. So if you want to migrate a brownfield project, a typical monolithic project, you have normally to refactor the whole system into an event-based system, and then you can put it apart into different functions. And that's not very easy. So it's serverless works very well for microservices if you can start on a green field, but if you are on a brown field, it's kind of hard work. For containers, it's the opposite around because it's very easy to move something existing. You only have to package it and bring it to the cloud. So if you talk about the kryptonite, so what is not so good about these technologies or what are the bad side, for serverless, it's, as I said before, it's very hard to migrate from brownfield monoliths to function as a service. And normally major refactorings are needed. On the other side, for containers, the step learning curve with multitude of choices along with significant day 2 operational overhead is very hard. So it seems to be easy to set up or to work with Docker, for example, and to use Kubernetes. But when the system is growing, it's getting more and more complicated. So this is what I mean by day 2 operational overhead. Okay, let's take a deeper look at scaling, because I said scaling is very easy on the serverless side, and as we will see here, if traffic increase, another instance of Lambda will be raised and the traffic runs against the other instance and so on. So it scales by purpose. Of course, you have to keep in mind the cold start issue. I guess you all know about the cold start issue. So if the instance cannot be reused for any reason, or you have to start a new instance, you have a certain overhead, a certain delay, which is not so small, and you may run into a cold start latency that is too big for your use case. And if the case is like this, you have to keep the instance alive. You have to trigger it all the time, for example, to ping it all the time, or if you're not in the AWS cloud, there's a mechanism that you can keep them alive by configuration, but this means you have to pay some extra money for it. So you can, for example, when you know your traffic, you can say during daytime from 9 to 5 or something like this, I need 100 instances in parallel, or 10 instances or whatever, but you have to pay for it to keep them alive. Okay. When it comes to the container side, it's a little bit more complicated. On this slide, I compare the AWS Lambda, serverless technology of Amazon, and the EKS, which is the Elastic Kubernetes service also on Amazon. And for the Elastic Kubernetes service, you need first of all a K8 master. And in addition to this K8 master, to be able to run your containers inside a pod, you need a node, a K8 node. So if there is normal traffic, you have this K8 master, you have at least one K8 node and a pod running in it and containers running in this pod. And if traffic increases, you spin up another pod, a second pod, and The question is what happens if the traffic increases again at this moment. And what happens right now is we spin up a new node, which is a new VM, EC2 instance, and place a part with its container inside. And as you can see, the problem of this approach is that the node that we just established is only 50% utilized, but charged for 100%. So we have to pay the full instance, but use only 50% of it, or maybe 10% or something like this. So if the traffic is unpredictable, if we do not know if we have to scale or not to scale, we may pay too much money at this point. And if you take a look at this slide, it seems that when it comes to cost, that lambdas may be the better solution. And that's what I want to show here. If we take a look at traffic like 3 million calls in a month with a memory amount of 512 MB and 300 milliseconds of execution time, we see an unpredictable traffic, which means there's not a linear traffic, but there may be peaks. We have on the serverless side $8 per month. There's a calculator for this. You can type in the values and it will calculate it for you on the AWS website. And if we use the container orchestration scenario, as we've seen before on this slide, for the same traffic, we have something about $160 a month. So it's much more expensive. And this is because we need this master node, the control panel, and then because of the and we have this additional small worker node. And this may become much more expensive when there are peaks because, as I said before, we need another EC2 instance or maybe 2 more EC2 instances. And then we have additional 14-something dollars for every instance we need temporary. So this example, the first example showed that serverless seemed to be less expensive, much less expensive than the orchestration counterpart. But if we take a look at another scenario, like the second one, we have 90 million calls a month, we have different amount of execution time, and we have predictable traffic, not unpredictable, but predictable traffic, then we can see that the orchestration part could be less expensive than the serverless part, because when we know the kind of traffic, when it's predictable, we can choose the right kind of VM, the right configuration of VM, and this is this part over here, and we don't run into the scaling issue I showed in the first example. So the answers, which is less expensive, it depends. It depends on your payload, on your workload, and on the predictability of the traffic. So you cannot say that one solution is cheaper than the other, but it depends on the related patterns. So the conclusion is when to choose what, or when to choose serverless, or when to choose container. Serverless is best suited when you bring your own business logic and want to combine it, integrate it with other cloud services. When you have an event-driven architecture, when the traffic is unpredictable, and when you work with greenfield projects. On the other side, when to choose containers, when you bring your software with dependencies, and dependencies could also be servers, web server, app server, or something like this. When it's more request-response driven, the traffic is predictable, and when you're, for example, migrating an existing system to the cloud. Also, when portability is in focus, so you want to run your container infrastructure in one environment or in another environment, and when you need control, or when you think you need a lot of control. So to bring it together, it shows containers and container orchestration when you need flexibility and control, or when you need to migrate legacy services. And on the opposite side, choose serverless when you need speed of development, because the learning curve is much more flattened, and when you need automatic scaling and significant lowered runtime cost with unpredictable traffic. But normally it's not the one against the others, but you can combine both if you want, because if you put everything in the same close, you have minimum latency. So choose hybrid whenever it makes sense. And this is what we do for our customers normally. We really take a look at if the workload is suitable for serverless or not. And we only choose the serverless technology when we are 100% sure that it's suitable. So the question is, what is suitable? What are typical suitable scenarios? This is the next thing I want to talk about, suitable scenarios. And the first scenario, I'm quite sure everybody of you knows, because it's kind of hello world in the serverless world, is putting data or file or something into the storage system that will trigger an event, and you listen with your AWS Lambda to this event and do something like image manipulation, thumbnail creation, PDF generation. I always talk about AWS because we mostly work in AWS projects. Of course, this will work also for all the other cloud function technologies like Google, Microsoft, Oracle, or whatever. Okay. There is Oracle out there. So how does it work? In my example, I want to upload an image and create a thumbnail out of this image. So what I do is pass an upload image call through an Amazon API gateway. This will translate my, my HTTP call into an event, into an AWS Lambda event, trigger my event. That event will store, or this AWS Lambda will store my image inside an S3 bucket. Of course, I can use a shortcut without this AWS Lambda if I want. But the important thing is right now, putting something into this S3 bucket will raise an event, an S3 object created event or put event, and I can configure special Lambda to listen to this event for this bucket, for a certain key, for example, for a certain prefix, which means kind of folder structure. And then I can take the image and do something with it, manipulate it, create it somewhere, and place it back inside an S3 bucket. Of course, the target S3 bucket should be another bucket or at least another prefix inside this bucket to avoid recursion or recursion. Okay, so this was hello world. Second scenario is streaming data, frequently processed stream data. And we use this in our projects, for example, to do trend analysis on social media streams. We grab social media streams and look for special information and try to evaluate trends, or we use this for sensor data monitoring and for anomaly detection. So if there is a production line, for example, producing sensor data, or a car producing sensor data, we grab this information, put it into a stream, and evaluate it. And how does this work? We see it over here. There's this is a sensor creating some data, uploading it to the stream system, which is in AWS, a Kinesis stream system. And then we have a Lambda function grabbing data every, for example, 100 chunks or 200 chunks or whatever, and processing this data. And of course, processing this data could mean checking for anomalies, for unknown values or whatever. You can also, for example, monitor your logs, looking for errors, for exceptions. This is nearly the same mechanism. And then putting the analyzed data or the aggregation of the result of your analytics into the Amazon DynamoDB, which is a NoSQL database, and use analytic tools to evaluate this. Both scenarios we already saw are very focused scenarios. So the first one was putting data or putting a file or whatever to a place and react to this and do something. And this one was, the second one was filling a stream, getting the stream data and doing something with this. But what about scenarios like a whole web application, for example, your auction platform? Is this suitable, or what does it mean to going full serverless for a platform like this? Going full serverless means, first of all, you need a content delivery network to deliver the static content or the PWA to the end customer. Then you need something like a BaaS, backend as a service for authentication and authorization. And of course, you need to implement all your business logic of the application, which you can do with FARS, with function as a service, using PaaS, using platform services like databases, storage systems, and so on. And if we take a look at this scenario, it would be like putting your static content into the storage system and having something like a CDN, content delivery network, to deliver the content, which is in AWS CloudFront. Then, as I said before, you have BaaS, backend as a service, for authentication, authorization, or for authentication, not authorization, which is in my case Amazon Cognito, where you can sub user pools and combine users with applications, access rights, and so on. So what you do is deliver the content, then the user uses the web page to log in with his credentials against Cognito, and he will get back a JET, a token, to authenticate and authorize against the application itself. And normally what you do is you put an API gateway between your back-end services, your cloud-based back-end services, and the front end. You do this for several reasons. The first reason is that you cannot access a Lambda function directly from a web application except you use a special SDK, which is possible. But if you don't use a special SDK, but only normal HTTP calls, you need this API gateway to translate the calls into Lambda trigger, as I said before. So you have a REST call, for example, and you translate the HTTP REST call into a Lambda trigger, which has different payload normally. In addition, you can use the API gateway for several tasks like API key handling, throttling if there's too much traffic coming on, like proxying, logging, tracing, request response mapping, and staging functionality, and so on. Okay, but I don't want to go deep into this or deeper into this. I just wanted to show you that it has much more functionality than only translating the call into an event. So, but after translating the call into a Lambda trigger, what happens? The Lambda trigger triggers, for example, storage-related functions or database-related functions, and then in the background we may have something like asynchronous messaging or notification services, or something like AE, artificial intelligence, or whatever. So we can use all the facilities of the cloud services. And of course, it is possible to do this. But if we take a look at the reality, the question is, does it make sense? So technically, it's possible to build up a web application, but the question is, does it make sense? And to answer this question, I want to take a use case as an example from this serverless showcase. This is kind of image diary. So if you travel around, you can take pictures and upload these pictures. Your friends are able to see these pictures, and you can tag the pictures with, like, for example, weather conditions, location, and stuff like this. You can give a description, so you have relational data and you have typical NoSQL data. And just take a look how we could build up this very small application compared, for example, to your auction application. This very small application into a serverless application, how many effort we will need to do so. And because this application is built up like a typical CRUD application, we need something like post, get, put, delete calls through this API gateway for images, because it's all about storing images and additional information. So we have one Lambda for create image, we have one for read images, we have one for update image and one for delete image. And these Lambdas will be integrated with the relational database for title and description, for example, with the DynamoDB database for image metadata, this was the tech data, and with the S3 bucket for the image itself. But because we do not work only with images themselves, but also with this metadata and with this relational data, what you normally do is you split up the different functionalities to avoid runtime costs, to avoid problems while working with all of the backend services, the platform services. What you normally do is you split them up in one create image info, one create metadata. So for this very small application, we already have 12 Lambda functions without authentication authorization. We solved this problem before. And what we also want to do is, for example, generate a thumbnail, so we need some additional Lambdas. And of course, we want some transactional behavior. So for example, if I upload an image with metadata and with description and so on, I want to do all of this or nothing. So I need special coordination functions called step functions in AWS. So the image will become in reality even more complex than that what we see over here. And the question is, does it make sense or not to do so? Because this, what we see here is a highly distributed event-driven system, highly distributed event-driven architecture. And for those of you who have ever worked with an architecture like this, they know it's one of the most complex architecture you can work with. And I will show this on a special use case. So we pick up one use case, which is upload image. So what do we have to do if we upload an image? As I said before, there's this gateway, and the first thing we do is store the raw image, the image itself, inside the database with one, inside the storage system with this one Lambda function. Then we store the non-relational information inside this DynamoDB, and normally there's another part, but it's not PowerPoint. It was not possible to place it here in this PowerPoint slide for the relational data. So there's 1, 2, 3, and then we need something to coordinate the transaction, which is a step function, and then we have this additional Lambda for storing the thumbnail, for creating the thumbnail and storing the thumbnail, and we have something like AWS Lambda triggering some subscribers, because it's possible in this use case to, or not only in this use case, in this application, to subscribe if you're, for example, interested in images from Paris. You can subscribe yourself and you will be notified if there's a new image from this location. So what we have to do, if there's new data for Paris, we will inform the people who are interested in. And then we have some additional infrastructure, like I said before, Cognito and the AWS Identity and Access Management System. We have CloudWatch, which is the logging system and metric system for operational overview. We have something like Amazon Route, which is a routing system combined with load balancers to bring your URL to the right gateway instance, for example, reduction, versus integration, and so on. And we have, last but not least, CloudFormation and a lot of stuff more. So it's not only about writing your code and bringing it to the cloud when it comes to split up a web application, but it's a lot of more work, as we can see over here. So it's not only about run code, but run code, not servers. It's you have to take care, or it's not NoOps as I always say, but it may be less ops, but you still have to do a lot of work, as we see, especially the work that's not inside your system itself, but out of the range over there. Okay, so let's take a look at what can go wrong with a system like this and how we can handle situations. Okay, first of all, of course, the client could send you wrong requests with wrong payload, for example, wrong headers, wrong JUT token or whatever. And you have to be able to take care about this. There could be a denial of service attack, so millions of calls. And you have to be able to control this. Then, of course, you can have bugs in your implementation. So your lambdas will not work, and because they do not work, they will not trigger events that triggers the next lambda, or they will not raise event that triggers the next lambda. And because we are in a highly distributed, event-driven architecture, you cannot see this problem in your response, because you get no response normally. So you have to, for example, watch your logs and automatically watch your logs and react on error messages. Then, in my special case, because I have this step function, we can run into transactional problems. Maybe we are able to store the image, but because of wrong privileges for the DynamoDB, we are not able to store the metadata. And of course, we cannot establish real transactions as we know them from database systems, so we have to implement a compensation lambda. So there may be a second lambda next to this lambda only for compensation if something went wrong. There may be a second lambda for every lambda you have to compensate the business logic. This is asynchronous communication, so we do something, which is our primary use case, and doing something will trigger or will raise an event asynchronously, and this will trigger a secondary use case. And you have to be aware if this works or not. It's asynchronous, so you did not get a response, a synchronous response that you can handle, but you, for example, have to take a look at the result, or you have to take a look at a dead letter queue if there's an event inside this dead letter queue indicating that something went wrong. And it's your responsibility to do so. It's not the responsibility of the platform. And this is, we can run into timeout situations because we call some lambdas. We have set timeouts for these lambdas. None of these lambdas run into a timeout, but because of chaining more and more of them, for example, we have 3 in a row and waiting for a result or something, we run into a timeout for the gateway. So the response for the end user runs into a timeout, but none of the lambdas themselves run into a timeout. And you have to be aware of this. Of course, we can have issues with privileges and user rights management. We can have routing issues that we route to the wrong stage of the gateway. And this is good. We can have problems inside our gateway itself. It's kind of complicated to configure your gateway in the right way. So maybe you have wrong security mappings, you have maybe wrong payload mappings, so the Lambda functions cannot work with the translated payload, with the triggered payload. You run into version problems and so on. So a lot of possibilities for problems, and we work inside the cloud, so the cloud itself could become a problem. Outages, availability of certain components inside the cloud, cost limit explosion, for example, so you cross a limit without being aware of it, region problems, and lots of more. So this is an overview. So they said run code, not servers, and it will be fun. And if you take again a look at the slogan from AWS, run your business code high available in the cloud in response to events and scale without any servers to manage. For me, it sounds a little bit more like run your business code highly distributed and event-driven in a non-transparent environment with no single point of control. And this is what we have to survive. And so writing one Lambda is very easy. So you just have to take a tutorial and it will work. But combining them could become very, very complex, and keeping them under control because of this event-driven mechanism and asynchronous approach could become very dangerous. So you really have to take care about this. And I found a small image or animated GIF inside the internet, which is for me symbolic for the serverless cloud work. So this is like serverless works. Everything seemed to work, but you don't know why. And for example, if I remove one of these people, you never will mention it. So the real task about serverless is not how to develop, but it's how to test and how to monitor. And for the last, I don't know, 30 minutes or how many time is left, for the last 30 minutes, I would talk about this testing issue, how to test serverless. What is different in testing serverless applications compared to your regular, for example, monolithic applications. So how to test. Famous Lars words, shouldn't be too complicated. And when it comes to testing, what is testing about? Testing is mostly about gaining confidence in your code running as expected on a specific target platform. And in our case, the target platform will be the cloud and the serverless runtime. So gaining confidence that my stuff is running inside the cloud as expected. And testing is also about minimizing the risk that something unexpected will happen in production or on the target platform. And we will see that it's very important to keep in mind target platform, because when it comes to tests, you can test nearly everything today or simulate everything inside your computer, but it's not the target platform. It will never behave like the real cloud. So it's very important to do at least a part of your testing inside the cloud itself, inside the target cloud with the same environment configuration. Okay, what does it mean in a serverless context? Again, it's about gaining confidence in our code and minimizing risk of failure in production. And if we take a look at the traditional way of testing, the traditional testing pyramid, we see that most of the effort we normally put into, not most of the money, but most of the effort we normally put into unit testing, because there's our value, there's where we can find our business logic. In the serverless world, it's a little bit different, because the serverless function itself is normally very small. So the business logic, the portions of business logic are not too complicated, and so they're not too complicated to test. But the real complexity is in how my serverless function interacts with the different cloud components, different cloud services with other lambdas. So it's nearly all about testing this interaction and this integration. And so if we take a look at what may be the risk, we talked about minimizing risk. We may have a configuration risk, like the database tables are not correct, the names are not correct or whatever. I don't have the right access rights. When it comes to technical workflow risk, it's, for example, I'm parsing an incoming request and the payload of this incoming, or the payload is not as it should be, or I'm not able to handle a response and translate it into a successful HTTP response or an adequate error. Business logic, like programming errors, and integration risk, which means corresponding with the other cloud components and cloud services. For example, I trigger an event and I'm not able to handle, or the Lambda is not able to handle the event. So the biggest risk is not in business logic, and it's also not about configuration and technical workflow, but integration. And this is why the testing pyramid looks a little bit different normally in the cloud environment. It's a little bit more like a honeycomb, and you should concentrate or focus on integration. Before I go more into deep, what are the best practices to do so, I will first just run over the different parts like unit testing, integration testing, and so what this means for serverless functions. So unit testing for serverless functions makes sure that your business logic is working as expected. And this means testing your business logic for errors and typically for coding errors, or business logic errors or coding errors. And what you do for this is, we will see this later on in best practice in more detail, is separate your logic, your business logic from your infrastructure. Because when there's an event triggering your serverless function, you normally have a lot of infrastructure code because it's a special cloud event, and you take this cloud event with the help of a serverless handler, and you have some context inside this handler which is proprietary for the serverless platform, and then you have your infrastructure, your business logic. And if you separate this, it's very easy to test the business logic by its own. If you do not separate it, it's very hard to do so. And of course, you can mock dependencies like all the cloud dependencies. And if you work with Java, you can do this with JUnitTest and gMockito. If you work with JavaScript, there are other frameworks. Integration means make sure that integration with other cloud components, make sure that the integration of your serverless functions with all other cloud components and services works as expected. And what you want to test there is, for example, that your DynamoDB query really works, that there's not a syntax error or something like this, that the response format is in the correct, or that the response has a correct format, so you can translate it inside your API gateway to an HTTP response, and so on. And what you can do here is using the cloud components from the real cloud components inside the cloud. So what you can do is build a kind of dev stage or test stage inside the cloud and run everything against this real components. But this, of course, can become kind of expensive if you spin up a database, which is expensive, and use it all day long for test. It will cost you a lot of money. So what you normally do is you mock or fake these cloud components. There are a lot of tools doing so. There are local pendants to the cloud infrastructure like DynamoDB local, like Kinesis Lite and so on, or S3 server, and they are fake components. The difference is, for example, DynamoDB local is really a local instance running on your server, on your laptop, for example, and something like fake SNS is not a real service, but it's a mocking service. So you can run API calls against it, and will get a predefined result. Okay, we will see this later on in more detail. And end-to-end testing means testing your user source, and this means make sure that the chains of serverless functions and cloud components work as expected. So if you chain more than one Lambda triggers another one, or will as we saw with this thumbnail generation, one Lambda puts an image into an S3 bucket, and the S3 bucket raises an event, and the next Lambda reacts on this event and creates a thumbnail. We want to test this. And what you test there is, for example, wrong permissions, or something like timeout that are not set correctly for the chain, or maybe memory allocations. Again, you can use cloud test stages for this, which again may run you into a lot of cost, or you can use local cloud emulations. But as we will see later on, local cloud emulations will be kind of limited. So you cannot emulate or simulate everything they have of these cloud emulations, but at least parts. And what we can use for AWS is something like SAM local or local stack or serverless offline, which are 3 different frameworks to do so. Okay. So let's take a look at some best practices. So how to bring this to work, what I explained before. The first best practice is to separate your business logic from infrastructure inside your function. We will see this picture for the next slides on every slide again, and what I tried to show is this is your computer. The left side is your computer, which means on premise. The right side is the AWS cloud environment, and in the middle you will see your serverless function. And your serverless functions normally consist out of handler function. This is the main entry point that is triggered by any cloud components, and then your business logic, which is the part below. Okay, so the first thing is separate business logic from infrastructure inside your functions. And if we take a look, I hope this is readable, at a typical handler, this is a greeting handler saying hello. So you put in a request with my name is Lars, and it will respond with hello Lars. And what we see here is that we mixed infrastructure code and business logic. So we have something like a Lambda logger, we have something like a context, which is AWS cloud specific, and we have something like creating the greeting response with string format, hello, first name, last name. We extracted first name, last name with the help of the request object. So we mixed both of these words, business logic and infrastructure, and this is kind of hard to test. If you want to test, you can only test the handle request. This is a minimum unit to test because we have no separated code, no separated business code. And so if we want to test this, we need a Lambda logger and we need a context. And what you normally do is just to test your business logic is to separate it. For example, to bring it to an own service called greeting service in my case. There's a greet function, so it's very, very easy to test this stuff standalone. And even if we want to test the handle request function, I put this log context info, so I separated the logging information into a different method, so it's easier to mock it later on. So when we take a look at the test itself for the greeting service, it's a normal unit test without any infrastructure code. And that's a good thing about separating it. You can test your business logic without, as it runs somewhere else, not in the cloud. So the next thing is mock cloud infrastructure components of your function. What we tested before was the correctness of the business logic itself. And what we want to test right now is the correctness of the handler function. So if somebody calls a handler function with a request, we want the response to be in the right format. And if we get a bad request, for example, we want to have a response reflecting that there was a bad request. So as we see here, handle request. So what we want to do is test this handle request. And in contrast to, or the problem still is that we have this cloud-specific elements, this infrastructure-specific elements like the context, which is an AWS thing, and the Lambda logger, which is also an AWS-specific class. So there, if we would take a look at the imports, we will see in Amazon something import statement. To get rid of this, what we can do is use, for example, cloud-agnostic components. We can use special log manager. We can use log4j logger in this case, and this is easy to test on our local machine. Or we can use fake infrastructure components. This is what I do here. There's an animation. So what I did is, inside my test, instead of using the real context object from the AWS, I implemented a test-specific context, and I can reuse, or I can use this test context for all my tests. And then I call this greeting response. Response is class under test, handle request with request in my test context, not the real context, but the test context. And so I will see if the response and the request match to each other. This, of course, means kind of a fork, because I have to re-implement the logic of the cloud infrastructure for my test, at least the parts I will need. What I also can do, of course, is use mocking frameworks. It's common practice, like Mockito or what else. So what I do here is I create a mock context with the help of the mock or of the context interface, and I define what I expect the mock to react on when there are special calls, and I can test with this. Okay. So the next best practice is use local environment for functional testing. What we want to test now is if we trigger our Lambda. So we want to trigger our Lambda with correct input and with correct events, and this should lead to a correct result. So not just calling the function by itself as we did before, but not the handler as we did before, but really trigger it. And if we want to trigger something, we need an environment, a runtime, at least a dummy runtime. And this is where SAM comes into the game. SAM is a serverless application model, which is a kind of description of your environment. It looks like this. So what I do here is I describe my environment, which means up here I see my serverless function itself, Java-based, with some additional information like timeout, environment variables, and so on. And I see the gateway information. So I describe my environment, and what I can do is I can start this and locally establish this runtime environment with a lot of limitations. As far as I know, we will see this limit or parts of this limitations in the next talk, right? Yeah. So you have to do it because I said it. So how does it work? There's a special CLI for this called SAM, and what I do here is calling SAM local, which means started on my local machine, and then I have a special call for it like invoke, which means invoke one of my lambdas defined inside my SAM YAML template. And in my case, this lambda function name was greetings. So when I go back, I hopefully have something like greetings over here. Yeah, you can see it right, the line 3, greetings. This was the definition of my lambda with name greeting. So I call this greetings, and then I say I want to call it with a special event, which is it lays on my local machine called event greeting JSON. And if I want to, I can set several environment variables like memory size or whatever, or put in some environment variables, additional environment variables. And what this will do is start a local Docker container running my payload inside this, or my serverless functions inside this Docker container with the help of this event. And as we see here, greetings, this is the answer, greeting, hello Lars Röwekamp, I'm pleased to meet you. So this is a nice way to check if your Lambda functions with a given event triggered with the same triggering event mechanism like you will use in a real cloud, if it works like expected. And of course you can not only test the positive but also the negative parts. So running into problems. What we did in the last example is we just triggered it, but normally with a self-generated event. But what you normally do, with a self-generated event. But what you normally do is, in the real world, is calling your Lambda with the help of another component. So the other component will trigger the event or raise the event and trigger your Lambda, or with the help of the gateway. So there's an application sending a REST call. You translate the REST call into an event, and this event will trigger the Lambda. And if you want to test this, you can also use AWS SAM with a little bit different mechanism. You just start the gateway. Maybe you remember, I think it's not on this slide, I go back to this slide. We had this section here, create resource, type API, which means API gateway, and for the past greetings, there should be a method available post, and this is where we define, on the one hand, the gateway, how it works, and the reference to my Lambda function over there. So, and with the help of this, with a bigger SAM template, for example, I can define a whole CRUD application using databases in the background or storage system or whatever. Okay, going back to this. So what I do right now, in contrast to this example, this is only a one call, triggering one call, starting all the environment and tearing it down afterwards. And what I do here is starting my gateway, and the gateway is ready to take calls from outside. So outside means from your computer. And what I can do right now is, so this is starting the gateway. What I can do right now, it started listening to port 8080 on my local machine. What I can do right now is just send a normal call with the help of my web application or with the help of Postman, like I did here. And as you see, I send a first name, last name, which is just a JSON call to the backend system or to the gateway, and we'll get back this response. And of course, I can do this automatically inside my test automation and also automatically test the responses. And what happens in the background is that the gateway takes my CRUD RESTful call, translates it into a special gateway format of event, and send this event or triggers with the help of this event the Lambda. And this is what you see here. This is the translated call. This is what ends up in my Lambda function. Okay. So what we did so far is we tested the business logic of the Lambda. We tested the handler itself, that it works when it's triggered by a self-created event. We tested the Lambda function triggered via gateway that created the event or translated the call to an event and triggered the Lambda. And what we want to do right now is test the integration with other components than the gateway. For example, the database, the storage system. And we have to take care about two ways. The first way is when the cloud service triggers our Lambda. And the second way is when the Lambda function wants to correspondent or work with our cloud component. So for example, I put something in my database and I want to react the Lambda of this new data. And the second case is the Lambda should store something in my database. What I want to do right now is just test this behavior in my local environment. We're still in a local environment. Okay. And it's very important to understand this. Technically, this is possible for most of the cases, for most of the cloud components, but this can only prove functional correctness, but not infrastructure correctness, which means that you cannot test that letter queues. So what normally happens if the AWS cloud is not able to bring this, to trigger your Lambda for any reason, because of limits, you reached a limit or timeout or something like this, it will put the event inside a dead letter queue, and you can parse this dead letter queue if there's something inside, and you can react. You can use another Lambda, for example, listening to this dead letter queue to the event that there's something ended in, and take this value and do something with it. And this is something you cannot test. You cannot test timeouts, you cannot test throttlings, you cannot test SLAs, and so on. So it's only about the functionality integration, but not about the infrastructure itself. And trust me, a lot of problems occurs because of the infrastructure, not because of the business logic. Okay, what you do here is first I want to, for example, test that putting something in my S3 bucket will trigger will trigger my Lambda in the right way. What I can do first is just use SAM local again to generate a corresponding event. Like we see over here, I can say SAM local generate event S3 put, which means this event simulates that I put something inside my S3 bucket. And then we see the event created, and we can use this event to invoke the Lambda function, as we saw before. This is This is the other way around. This is triggering or corresponding with a cloud component, cloud service. And in my case, I started a local DynamoDB. So the DynamoDB, the NoSQL database, is now running on my local system, on my local machine. And I can create tables or delete or insert data or whatever. And the only thing I have to do is make this available or redirect the call that normally will go to the real cloud, that they will go to my local environment. Do this like with the help of the AWS CLI by saying, only inside my test, of course, by saying the endpoint URL is localhost 8000 and not the cloud environment. And I can, for example, in this case, call DynamoDB calls like list tables and so on. And this works on my local machine. And I can use the same mechanism to test, to redirect the calls inside my AW Lambdas. What I did here is something I can also do with the AW Lambda or with the DynamoDB SDK inside my AW Lambda. So the only thing I have to do is redirect the call, and then it will work. The Lambda will work with my local DB. But as I said before, this will only test the business logic, the integration part of the business logic, not the infrastructure. So what we normally do is take the same SAM YAML or parts of it, of the SAM YAML for use cases and span of a temporary integration stage or a temporary integration environment inside the cloud. Why temporary? It's a question of cost. If you, for example, establish a database with huge amount of data and a storage with huge amount of files in it, for example, it will cost a lot of money. So what we do is we, just for the integration test, we build up this environment, do this end-to-end test or this integration test, and then tear it down again. And this is kind of easy with the help of SAM. But this is normally not enough. What you also need is a real-life copy or a real copy of your productional environment. This is what we normally also do, is a permanent integration stage. And this is very important to understand when you calculate your cost, because especially when you're a huge company, AWS will come to you and do some cost calculation, and they ask you for your productive traffic, your normal productive traffic, and then they will do this cost calculation. And in general, it's much cheaper than your current cost. This is because they do not calculate, for example, this permanent test environment. They do not calculate that you do a lot of work or a lot of development inside the cloud itself. So do yourself a favor and think about real-life scenarios, how much part of your testing you will place inside the cloud, if you want this permanent cloud environment or not, and calculate with these facts and not with the current runtime facts. Okay, so are we done with this? And the answer is no. we're not done testing don't end with shit deployed, but you also test when things are in production. And what does it mean, test when things are in production? I said, if you remember the beginning of this part, it's all about testing, is all about gaining confidence. So what could happen? Outage of the cloud and cloud components. And I want to be sure that my stuff is deployed, but the cloud is not working. I integrated some third-party services, some third-party apps, and they do not work as expected. And because of, for example, scaling issues, I run into problems. And of course, you may say, hey, we're inside the cloud, so this will never happen. An outage of the cloud will never happen. But take a look at this. AWS outage killed some cloudy servers. Recovery time is uncertain. This is only a year and a half ago, and this happens not often, but it happens. And normally it happens only for a second or something like this, or for several seconds, but as we saw in this case, a lot of very, very huge companies were involved in this problem. And what you want is to get aware that there's a problem at least and react to it. And this means you must monitor your system, which is very important. And you can do this with the help of robust monitoring and error reporting, which means you need a logging, tracing, metrics, alerting, which is another talk to get aware of all the pitfalls of this stuff. And it's mainly about anticipating of disruptions and automatic recovery. So you do not want to run into the problem, but you want to be aware that there's a problem arising before it really occurs. That's very important. By just by collecting metrics and comparing metrics, by establishing alerts. If there's a threshold, if you reach a threshold, for example, for your storage system, then you can automatically scale or automatically recover. Okay. And then you can also use chaos engineering, inject small doses of failure into your system and see how it reacts. This is, for example, what Netflix does in their microservice-based system. They just turn off some of the systems and hope that it will still work. Maybe not their streaming service, but nearly all the other services, they do this just to see if their resilience patterns really work as expected. Okay. So, last slide, or two more slides. Conclusion, how to have fun with serverless. As we have seen, serverless may be a lot of fun, and we will see this in the next talk again, I hope so. But there could also be a lot of pain. It's not only about writing your code, uploading it to the cloud, and everything works fine. You still have a lot of things to keep in mind to take care about architecture, patterns, and so on. And especially, it's very important to find suitable serverless workload. If you do not find the right workload, if you try to do everything serverless, you will run into huge problems. And at least your customers will run into huge problems because, for example, latency, cold start latency and stuff like this is very user-facing. So your user will be aware of this and he will not be, or they will not be happy about this. And it's about applying the correct integration patterns. Okay. That was my missing manual about serverless. Of course, there are much more topics to cover when it comes to missing manual. This was part 1 of 100 maybe, I don't know. For me, it was important to show that serverless itself, every single serverless function is very easy to implement by doing a productional application, finding the suitable scenarios, finding the serverless workload, finding the right integration patterns, doing testing right, monitoring right, may become very, very complicated. And we'll see after pizza, as I learned, we will see a real-life use case explaining exactly this to us. Thanks.
Thank you, Lars. Thank you for your great talk. Are there any questions? Take your chance now. Already so hungry. So no questions online as well? Oh, great, great, great. So in that case, we'll go into a short, yeah, okay, sure, sorry, please. Okay, here we go.
So you also mentioned this orchestration and stuff. So how do you go about then, or let's say debugging stuff when you kind of like have more like orchestration problems where it's kind of like, I don't know, I can imagine that like one part is synchronously doing something before the other, and it's like maybe like, you know, like typical scenario in the usual development, like where multi-threading or concurrency, so kind of like that.
Yeah.
How would you debug that in production then?
Okay, so I guess I do not have to repeat the question because you had a microphone and it will be also available on the streaming.
It's available. Yes.
Okay, so the question was about how to get aware of problems while coordinating stuff, orchestrating stuff, and this is a real problem. This is because of this event-driven asynchronous stuff, and what we do is a lot of monitoring. We monitor different systems, for example, dead letter queues. If something is inside the dead letter queue, we monitor the events that are raised and triggered, and take a look at if these events are the expected events. We take a look at results that we expect to arise when there's a certain request, and we take a look at, for example, if let's take this upload image scenario where we have two database accesses to DynamoDB and relational database, and also we have this image processing. So this means we have two accesses to the S3 storage system. What we do is when we get the result, take a look if there's something inside the database, or at least if there was an event of the database, and of the two databases, if there were two events of the storage system, for example, putting this together. And you can do this in AWS with step functions, which are kind of state engines. So every event changes the state, and you can collect the state changes and use them to moderate, to compensate, and to coordinate all this stuff. So you have a single point of control with the help of the step functions, if you want. And you can use this for debugging also. You can use SAM for local debugging, but it's kind of limited.
Yeah, I was thinking more in terms of production, right? So
yeah.
Basically, like, because it's like when you have a running system, I mean, like, it's usually like with the synchronous systems that you kind of have like, things that are usually not working then in production, that you basically have like maybe 1 in a million operations going to fail, so that's a bit harder.
Yeah. So what you do is you can also use tracing, like tools like X-ray or whatever, just to see if the parse you expected is gone through from start to end. It's a little bit hard if there are a lot of ways based on decisions. So if you can you go this way or that way or this way, then it's a little bit harder to keep this under control. But it's mostly about monitoring your system with the help of lambdas, for example, monitoring dead letter queues, monitoring logs, monitoring the end cloud components, end cloud services where you expect data to be put in, like databases or storage systems. Okay?
Anything else? In that case, for guys watching online, we will be back at approximately 30 minutes, and we will be live with our second talk, so just stay tuned. And for you guys, we ordered pizza. Have yourself a great pizza and a refreshing break. Let's be back here in 30 minutes. Thank you very much.
Great.
So welcome back from the break. Sorry for the short delay. We are broadcasting live here from the Serverless Meetup in Graz. Our next speakers are Martin Kammersberger and Sebastian Roof. They will be talking about the first steps to the cloud. So it will be our own learning journey at AURENA Tech, what we learned the past 6 months and with what pains and problems we were confronted. I'm very proud to introduce Martin Kammersberger and Sebastian Roof to you. Martin is one of our founding fathers at AURENA. He was there from the beginning, and he's our Angular expert. He is responsible for the real-time auction platform, and as I said, one of the first members of the team. Sebastian Roof joined us last year when we were just starting with our serverless journey. He's a very versatile developer, and he was really eager to work serverless, and he already became a really good cloud engineer. So give a warm welcome to Martin and Sebastian.
Development process on AWS. Yeah. So before we dive into infrastructure as a code, cloud development, cloud frameworks, and tooling, let me tell you a bit from where we started and why we decided to go for microservices and the cloud-native architecture. Just a little side note at this point, the following slides and information will only be related to Amazon Web Services, simply because we only use them as our only cloud provider right now. We will not cover Microsoft Azure, Google Cloud, or Alibaba Cloud. Yeah, there's Alibaba Cloud. So back in July 2018, when we released our platform to the public, we had a pretty common architecture. We had 2 monolithic Java applications, but they were written in a not so commonly used framework called netkernel. Netkernel is more or less microservices inside monolithic Java applications, and you can think of it like having your functions or functional resources being defined with a string resource identifier that you can call from anywhere within the system. So it's the resource-oriented computing paradigm, and it also has some kind of event-driven design in it. And AURENA is growing. We have higher concurrent user numbers, and then there's the need for more performance. And ultimately, at a certain point, there's the need for horizontal scaling. And unfortunately, the framework that we have chosen back then does not allow horizontal scale that well, mainly due to certain features like in-memory caching. So when you do a database request, we can cache it so we get better performance. And doing all this cache synchronization across horizontal scaled instances would have been horrific. So with all that in mind, we decided we took the decision to transition to a service-oriented architecture in the cloud. And it's important to know that back then we had no experience, no one in the team who had been in touch with cloud development or cloud-native development at this time. And before we could have developed any kind of applications within the cloud, we knew that we had to get familiar with all those tools that are out there. So where did we start? And we quickly found out that there is not a real guide for developers who are used to develop within monolithic applications, used to develop on a request-response basis. There's nothing to see or to learn how to develop within the cloud. And you can find a lot of blog posts and so-called best practices about certain topics, but with reference to Lars Röwekamp, there's still the missing manual. So we didn't manage to find a true handbook that goes from A to Z, that tells you where to start, and it covered all essential parts. So we said that first we have to build a prototype to see if our understanding of combining cloud services and architecting within the cloud is correct. So we built a simple proof of concept with API gateway, Lambda, DynamoDB, RDS, and I also think Cognito and IAM. And we did it by click configurationing all together in the AWS management console. And it worked. But we knew that these were only the first steps towards working within the cloud.
So to move away from our click configuration prototype to a reproducible and scalable way to set up infrastructure, we needed to define our infrastructure as code. And first I want to give you a definition of infrastructure as code. It is the process of managing and provisioning computer data centers like AWS through machine-readable definition files rather than physical hardware configuration or interactive configuration tools. So you can see infrastructure code as a descriptive model of your actual cloud infrastructure that is made up of those definition files. In general, infrastructure code allows you to manage cloud resources in the sense that you can create and configure new resources, that you can delete existing resources or connect resources with each other. As you might expect, the infrastructure code is normally put under version control, and it typically aims for more of a declarative programming style because you don't want to define every aspect of your infrastructure in every detail. Infrastructure as code is key for DevOps as it allows automated and repeatable deployments, also known as continuous delivery. It helps you to manage different configurations per environment, for example, your dev environment, your production environment, and it enables your development team to test applications in a production-like manner early in the development cycle. And therefore, you can say it reduces the problem of the so-called environment drift. I want to mention the principle of idempotency. It is a property that a deployment command always sets the target environment into the same configuration, regardless of the environment's current state. So in general, you can say good infrastructure code reduces your risk and costs as you don't have to do those manual steps, and therefore increases the reliability of your processes and your deployments. There are several infrastructure as code products in the market that are suitable for AWS. So we at AURENA evaluated some of them, and I want to give you a short summary of our findings and our experiences with them. The first one is called CloudFormation. Here you define your infrastructure code with YAML or with JSON. Here's a little example. And it is a primary format supplied by AWS for defining cloud resources. You have your template, and then you store it in a S3 bucket or save it locally, and then AWS CloudFormation takes it and creates a stack based on your template. A stack is a collection of cloud resources that are related together. And then those changes get applied, and having those change sets allows you also to do rollbacks afterwards, and you can see history of changes. But in our experience, CloudFormation templates tend to get large very fast, because you have to define a lot of details like roles, policies, and the relations between the resources, and there are not many good default values for set. So you end up, we think you end up with a code that is often hard to maintain, and the writing of the cloud configuration code is quite error prone and involves a lot of boilerplate code. And when it comes to more complex scenarios like nested stacks and cross-stack references, things get even more complicated. Which leads us to the next technology, AWS SAM. It doesn't only support you with local debugging, but you can also define your your infrastructure with YAML syntax. This syntax is more concise than in comparison to CloudFormation. You can see that this snippet gets transpiled to this large CloudFormation template, so the YAML is typically much more expressive because it supports more language constructs like better support for parameters, mappings, and outputs. And so it is, you can say it's an extension to CloudFormation. It also supports you for local debugging, as Lars showed us previously. When you ran SAM local invoke with your generated event, then you can set your breakpoints as you're used to in your traditional programming. It also allows you to spin up API gateway in a Docker container. And when your focus is on Lambda, DynamoDB, and API gateway, we think it works quite well. But when you have to use a more diverse set of services, then you will encounter the limitations of SAM, because you would have to emulate all those different services locally, and that can be quite time-consuming. The next framework I want to talk about is called AWS CDK. The main difference to CloudFormation and SAM is that you can define your infrastructure code in a common programming language, mainly Type, but other languages are supported as well, like Python, Java, or C#. Here you can use AWS SAM in combination with CDK for local debugging. AWS CDK comes with its own CLI. Important commands are CDK deploy, destroy, diff, and synthesize. And when you run the synthesize command, the CDK code gets transpiled to CloudFormation, to a CloudFormation template, and then AWS SAM can pick up this CloudFormation template and use it to spin up the Docker images, and therefore you can use AWS SAM in combination with CDK. A main idea of CDK is that you define reusable cloud components, so-called constructs. And here on the right side, you see a tree that shows the structure of a CDK application. At the top is the app construct, and then the stack constructs. App and stack are special subclasses of construct, and the tree nodes would be your actual cloud resources like Lambda or Gateway, S3 bucket. So you can practically use your object-oriented skill set to work with CDK or your object-oriented experience in programming. AWS offers you a construct library for common constructs like Lambda or API Gateway, and what you can do is you can adapt those constructs easily by just extending the classes. The next framework is called the Serverless framework. It supports multiple cloud providers, and it has own XAML syntax, which is again more concise in comparison to CloudFormation, but it uses CloudFormation under the hood with regard to AWS provisioning. And you can use raw CloudFormation in combination if needed. If you have any limitations or any problems with the serverless XAML, you can use CloudFormation as a fallback. It supports local invocation of lambdas, of Lambda code, and I want to point out the very active community. Here you can see a snippet of the GitHub project with 34,000 stars, so it's quite popular. And there are some IDE extensions available for serverless framework. Yeah. That's it, serverless framework. The last framework is called Terraform. It's created by HashiCorp. It has its own HashiCorp configuration language. It supports multiple cloud providers, offers a registry for modules. A Terraform module is a kind of a library. It is not based on CloudFormation, but uses the AWS API, so that's a difference to the other tools. And it's widely used across the industry. And here you see a code example of Terraform. It has some similarities to JSON. At the top you define an identifier for your resource, and then you fill in the different properties of your module. It supports really a lot of different cloud providers, not only the major ones, but also smaller ones like DigitalOcean, for example. Finally, I want to show you a comparison matrix we made to give you a feeling for the popularity. The Stack Overflow questions and stars on GitHub. You can see that Serverless Framework and Terraform are most popular in that regard, and CloudFormation also has a lot of Stack Overflow questions, but it is a little bit a category on its own because most of the other tools rely on CloudFormation in some ways. I don't know how many people use CloudFormation without further tooling. Then the support of multi-cloud, Serverless and Terraform support multiple cloud providers. the compatibility to CloudFormation with SAM, CDK, and serverless framework. And special features for local debugging came with AWS SAM and serverless framework. At the bottom you see a chart from Google Trends, and Terraform is by far most popular according to Google Trends, and then then CloudFormation and CDK with some distance. And according to Google Trends, serverless framework is not that popular. So which tool have we at AURENA finally chosen? We have, the decision was for AWS CDK, mainly because we can use TypeScript as one language for all purposes, because we already use TypeScript in our Lambda code and in our Angular front-end applications. So that was really appealing to us. And then the next thing is that features like the artifact store of Terraform or multi-cloud capabilities was not really something we were interested in, as we only use AWS. And then CDK is directly from AWS, and our assumption was that the integration would be quite good of the services, especially when it comes to new services like maybe you know EventBridge. So that was one thing, and it was quite newly developed by AWS and marketed as the new tool of choice when working with AWS. And as AWS is the market leader, our assumption was that the community should grow rather fast. Next thing is CDK can be used in combination with SAM, so that would cover the local debugging issue. And we saw the CloudFormation output as an advantage because we could import the CloudFormation template into other tools later on if we had any need for the other tools. Yeah, and when we started to work with AWS CDK plus SAM, it turned out that we had to write really long debugging statements, bash commands with a lot of parameters, and when you have multiple lambdas, that gets annoying quite fast. So we decided to make to improve our development experience by developing a little tooling for us, a CLI. The CLI should cover deployment, building our sources, support us with the local testing, and generate the boilerplate code for us. And on top of that, we created a Visual Studio Code extension as a wrapper around our CLI. Here you can see when you do a right click on a Lambda, you can start the local debugger, and it triggers the SAM commands, and you don't have to worry about the parameters and so on. So that was convenient for us. Or if you want to deploy a stack, you have the deploy command, or you can destroy the stack again. That are some of the commands. Or you can choose your the AWS account you want to work with. That's it.
So all of that sounds great, right? Having all of our tooling and processes in place. See, the decision for AWS CDK was, of course, based on guesses, blog posts, best practices, and books. We never experienced anything with it before. And I like to recall a phrase of a friend of ours who told us last year, "You're safe in the hands of the cloud." However, in reality, when the honeymoon phase was over and the more we worked with the chosen tools, the more we felt the pain. You can see it here. And our tooling was in good shape, and we solved some issues we had with it. And we could have continued building services with it. We had all essential AWS services covered, and it would have worked, but it would have been a bottleneck for us in the future when we would have tried to build complex infrastructures with it, where we share outputs or certain stuff across multiple services and stacks. So it turned out that AWS CDK was the wrong decision for us. And that does not mean you shouldn't use AWS CDK at all. It was just not the right tool for our needs. For example, we experienced that a lot of CDK issues popped up in the time when we used it. And sometimes we even had to fix it on our own. So we downloaded CDK and we had to apply Git patches that we created manually until they will accept the merge requests. So there was clearly a slow bug fix rate. There was a lack of community. Of course, the tool was new on the market, but the community was not growing that fast as we expected it. There was an incompatibility with popular tools like LocalStack. LocalStack is nothing else than an emulation of AWS and its services on your local machine, and it's running in Docker. So you could simply create S3 buckets and so on in your own machine, and you don't need to pay for it on AWS. Achieving dynamic infrastructure and infrastructure as code required over-engineered code because CDK relies on CloudFormation, and CloudFormation is limited by its syntax. When you wanted to achieve dynamicness, you had to create a Lambda that executes your own stuff during deployment. So the infrastructure as code was just exploding. And there was a misleading documentation. We had a case where one of our developers got stuck for about 2 days, and it was simply because he was missing a dot in his resource qualifier. And it only happened in the first place because CDK didn't output the resource qualifier, and there was a bug in or typo in the documentation. And even though we told the support that there is a bug, and they told us they're gonna fix it, it hasn't fixed or changed till today. So still the same issues in the documentation. I bet some developers already experienced the same. So how did we address the issues? We had to restart. And we decided to take the following steps. First, we contracted a cloud architect that will reevaluate the tools and all processes with us. We sacrificed the ability for local debugging for now because there was no other way. And we decided that we'll come up with a solution later on, or maybe there will be a solution out then when we will use it again. But at the same time, we took also the decision to put more effort into integration testing. Because when you don't work on a request-response basis, if you do everything with isolated components, you need to ensure the functional integrity of your code and of the infrastructure. And you can only achieve this by getting your code in the cloud, run integration tests, and if you don't need it anymore, destroy it. We migrated all Git repositories, build services, and deployment services to GitLab. And we decided to switch to Terraform based on a recommendation of our cloud architect. And it was already a quite good candidate in our own evaluation. So we thought, why not? Let's give it a try. And Sebastian will tell you more about Terraform.
So Terraform Part 2. I'll tell you something more about the Terraform CLI. First important command is Terraform init. When you run it, it initializes your Terraform working directory and it downloads all the modules you use in your code from the Terraform registry. The next command is Terraform validate, it validates if your code is syntactically correct. And the Terraform plan step generates and shows you an execution plan. Here's an example. It tells you every step that will be, every change that will be made in the cloud. For example, the creation of new resources, the change of resources, or when resources get deleted. And when you execute Terraform apply, those changes will actually be executed in your cloud environment or on AWS. The next thing are Terraform modules. I already mentioned them. You can go to the Terraform registry. It's publicly available, and most of the time the source code, you can look up the source code on GitHub and look and see if it fits your needs. When you want to use it in your Terraform code, it looks like this. You tell Terraform the name of the module and the version of it. So the version is basically a Git tag, and then you have to provide the required variables. So in this example, there are 40 input variables and 7 of them are required. And then this module produces outputs, and those outputs can be consumed by your other cloud resources. So that's how you connect the different resources. The next thing is Terraform Cloud. Terraform Cloud allows you to define workspaces, and those workspaces stores the state of your infrastructure and they are therefore accessibility for all your developers, and you don't have to store your state file on your local machine anymore. Most of the time you define different workspaces for your different environments, like production or your testing environment, and then you can attach different variables to that workspace.
So, as mentioned, we decided to go with GitLab for our continuous integration and continuous deployment pipeline, simply because GitLab is the leader in cloud-native continuous integration at the moment. They offer a complete DevOps platform, so from planning, managing your services, till going to production, monitoring them in production, or even defending them in production. They provide a lot of stuff. And to give you a glimpse about what GitLab can do for you, I will show you some parts of our infrastructure in a minute. The GitLab CI is based on a configuration written in YAML. It's based on stages and jobs, and they provide different workflows for your branches. So, for example, you have your feature branches, your review branches, or even the stable ones like production. And you're able to define different workflows for all of them. In our pipeline, it looks like this. So in the top picture, you see we build the source, we run unit tests, we do some Terraform operations to apply changes to the cloud, we run integration tests, and afterwards, we just destroy the infrastructure again. Again, this is important because running integration tests in the real cloud infrastructure is necessary to understand that your business logic and your infrastructure logic is working together. And the pictures below show you some parts of our GitLab CI configuration file, like defining variables, stages, how to include other GitLab CI files, or more precise, on the right side you will see our source build command. And yeah, it's just a combination of bash commands. But compared to 100 or 200 lines of bash scripts that we were used to run in our own Bamboo instance, this is a much nicer and cleaner way to document your CI pipeline, to run your CI pipeline, and it's also in your Git repository, so you have track of changes. And another great feature GitLab CI offers are multiple environments, like review, testing, staging, production. And this is in relation what Sebastian has showed you before. When you define environment variables for these environments, these get automatically passed to Terraform. So, for example, you define a variable inside Terraform, you specify it also in here. When you trigger the deployment, Terraform will pick it up, and you have your dynamicness. So what's the conclusion? We achieved a reliable and trustworthy infrastructure with Terraform. We do no longer rely on deployment bash scripts that were running in our own infrastructure on a Atlassian Bamboo. We've got an easy to reproduce and easy to scale infrastructure. We've got a reliable CI/CD pipeline with GitLab where developers can trust the output. And we do no longer rely on self-hosted on-premise Atlassian Suite anymore. So before we hosted Bamboo or Bitbucket in our own infrastructure, in our own company's infrastructure, we've got rid of it and just use gitlab.com. And last but not least, let's sum this up. We can tell for sure that starting with cloud development is not an easy task and can be, of course, a pain. And at first, we also thought, why the hell do we need this? Can't we just click configure everything in the AWS management console? We don't have such a huge infrastructure yet. This is just over-engineering. And now, after a couple of months of back and forth and, of course, trouble and pain, we can finally say that even though it has not always been easy, we're glad that we took the decision because we've got a reliable and easy to reproduce and scale infrastructure, and we don't need to worry that much about misconfigurations in the AWS console anymore. And the best of it, it's really finally starting to make fun developing and working with all of those tools, because when you have your pipelines in place, you can just code and everything works together. This is what we understand with cloud development. So we hope we could give you some insights, and thanks.
Thank you, Sebastian, for the great insights. Are there any questions? Anything else you want to know? Okay, great. Sure. Here we go.
So you headed in the wrong direction, and how hard was it to change this way?
Well, basically changing from AWS CDK to Terraform, it was a complete new tool and we had to get familiar with it. Luckily, a lot of the syntaxes or properties you define inside the resources are the same because all of them are using the AWS APIs in the end. So we had just to copy and match the key value attributes. But of course, it's not just like copy pasting. It was still a different structure working with those Terraform workspaces, but yeah.
There was a second
part. The cloud providers promote serverless with the slogan "Run code, not servers," and you showed in an impressive way that there's a lot of more work to do than only program your business logic. So what do you think, how much percentage you spend in developing business logic compared to caring about infrastructure?
I don't know what I should say now, but it was a heck of work to get everything together like this. Again, there was no manual, so we had a lot of time to invest to find the right path for us to work. And I don't know, I think maybe 10 or 15% business logic and everything else was just pipelining infrastructure.
Just make sure that's not your problem, because it's we had the same experience, so it's real life experience, and thanks for sharing this experience.
You're welcome.
Anything else? Okay, great. Thank you, Martin. Thank you, Sebastian. So I just want to promote the serverless event, the serverless meetup. There will be, it was not just the first, it was the first today, but it wasn't the last one, of course. We want to make at least 3 a year. If we can do it, we will we'll organize 4. So please, if you want to have a talk here, please just submit your proposal, or if you have a suggestion for a speaker you want to hear, also please let us know. We are happy about this, and of course we are especially happy about if you want to speak here at the meetup. I want to thank all of our speakers, especially Lars. Thank you for coming here, flying into Graz. And thank you also to the whole team organizing the meetup, live streaming. It was quite of a workload, but I think everything worked out really nice. I hope you guys enjoyed and had a great time here in Graz and online at the live stream. Thanks for being here with us this evening, and we wish you all the best and stay curious. Thanks.